Hello everybody and welcome again to the NPTEL online certification course on microelectronics devices and circuits. We will start with today's lecture on CMOS inverter basics part 1. So, that will be the lecture module which is supposed to be delivered now. It is CMOS inverter basics 1. In our previous interactions we have understood the basic principle or functioning of a MOSFET. MOSFET is a current source and MOSFET is a switch. We also understood the basic concept of threshold voltage, which means that the gate voltage above which for an n channel depletion in enhancement mode MOSFET the device is in the on state and below which it goes to the off state. We have also understood the region of operation of the MOS device in saturation as well as in the cutoff region, and we have therefore also appreciated all the second order effects which are available in MOSFETs, which come out because of under certain conditions of structural or electrical inputs. What we will be doing is we will be stepping now from a device perspective to the circuit perspectives, and we will start with today's lecture on CMOS, which is CMOS technology, also known as complementary metal oxide semiconductor technology, right. So, it is basically C stands for complementary metal oxide. We will see why is it known as complementary as we move along. So, let us just give you the basic outline which we are supposed to deal with it within this introduction. The first thing is basically the basic idea of a CMOS inverter, right. So, we will see what is the meaning of an inverter, because this is the basic building block for any digital or even analog VLSI design. So, for any of the chip or any of the circuit which you want to design, the prime notification or the prime building block is basically a CMOS inverter. So, we will understand what is the basic idea of a CMOS inverter, how it looks like, how it functions. We will look into the switch model of inverter, also known as RC switch model. So, we will be taking these resistances. So, these MOS devices, how these MOS devices tend to store a charge in the capacitance, acts as a current source, and then in a cutoff acts as an open circuit. And therefore, we will be looking at the static behavior of the device, which means that static behavior primarily means that you give a DC bias to the gate side of the MOS transistor and then see how does the current flow in the output of a MOS transistor. That is known as static, right. Whereas dynamic behavior or AC behavior is when you start giving a voltage and you vary the voltage from low to high value, then what is known as a dynamic behavior. We will also look at voltage transfer characteristics. Voltage transfer characteristics is basically the transfer or the profile between V out and V in. So, if I vary V in, how does my V out vary in a CMOS inverter is defined as a voltage transfer characteristics, right. And it gives us a many idea about how switching or how is the MOSFET is getting switched from on to off and off to on, and how is it helping me to charge and discharge a battery or external capacitor in the output world. With this, when we have understood what is a VTC and we have seen how a VTC works, we will be actually coming to what is known as a switching threshold. We will define switching threshold with perspective to digital logic as well as to analog logic, and see what is the meaning of threshold and what factors the switching threshold depend. Finally, we will be ending with noise margin and gain calculation. Noise margin primarily basically we will understand that how much amounts of noise can be inserted onto a CMOS inverter without flipping of the data. So, if a 1 is there, it is still read as 1. So, let me see how much amount of noise can I introduce into it, and that much amount of noise an inverter will easily reject and the data will not be corrupted. So, we will be actually looking at noise margins of the inverter, and then finally from analog perspective of view we will be actually doing a gain calculation, which means that we will try to find out del V out, right, del V in, that is what we find out AV. So, dV out dV in we will try to find out, and this is basically your voltage gain which we will be seeing as we move along. So, this is the outline or the basic outline of the talk, and let me come therefore to a basic CMOS inverter. Before we go to basic CMOS, let me give you the brief idea of what we had done earlier, so that it becomes easier if you to appreciate this point. If you remember in my NMOS transistor, if I had a gate voltage with me Vg, if my source was grounded and even if your drain is grounded, then Vg should be greater than equals to Vth of this device for this device to be on. It primarily means that for the device to be in the inverted state or in the on state, my Vg should be greater than equal to the threshold voltage of the device. In that case only my device will be in on state, but in the on state it is not necessarily that there will be an ID. As you can see, since your drain is grounded, you do not have any chance of any drain current flowing, right, and therefore ID can only happen provided you have a VDS, right, but at this stage VDS equals to 0, and therefore I take ID equals to 0, and therefore even if ID is equals to 0, the device is in the on state. So, whenever, let me recapitulate for an n channel device, when Vg is greater than equals to Vth, NMOS is on, right, and when, let us look at PMOS, whenever Vg is greater than Vth, PMOS will be always off, because for PMOS I require that this condition should be Vg as gate to source, and for PMOS the condition is that my VGS should be less than equals to mod of VTHP, right, that is very important. So, you see when for the same input signal, right, if my device NMOS device is on and I give the same input to my PMOS device and NMOS device, let us suppose this is my PMOS and this is my NMOS, and my NMOS is switched on by the virtue of the fact that this gate voltage at this point is larger than threshold voltage of the device. This will automatically ensure that my PMOS will be off. Why? Because PMOS you require a lower threshold voltage, or threshold voltage should be low in order to switch on the device. So, the primary difference between NMOS and PMOS is the very basic fact that for the same amount of gate voltage given to NMOS and PMOS, if means like in digital logic, if, which means that if VDD corresponds to 1 and VSS or V ground corresponds to 0, then when you apply VDD to both the gate terminal of NMOS and PMOS, the NMOS is switched on and the PMOS goes to cutoff mode, and whenever my VSS equals to 0 or my input is equals to VSS, then my PMOS switches on and NMOS switches off, and hence the name complementary, which means that both NMOS and PMOS will never be on together at certain, it will be on for a small duration of time, but for most of the voltage range, I will always get these to be as a complementary switch, complementary, right. What is the reason for complementary? Because both NMOS when it is on, PMOS is off, right, and vice versa, this will be vice versa, right. So, this is very important idea which you should always keep in mind, that you always have a switching of the threshold taking place in this manner. Now, to come into that fact, as you can see here, this M2 is basically my PMOS, this is my PMOS and this is my NMOS, this is my NMOS and this is my PMOS which you see here. Now, whenever my, and we obviously have a load capacitance here, this load capacitance is nothing but the overall capacitance of this part here, right, or this part between these 2 points and so on and so forth. So, all the capacitances in this PMOS and NMOS, if you add together, I get C load available to you. Also, C load can be the load capacitance which you are putting in the external world, or the load capacitance of the subsequent stage of the CMOS inverter, right, that you plug it and place it here, right. So, therefore, it basically means that the inverter at one point of time will be charging this C load and another point discharging. Let me see how it works out. So, when V in, maybe I can just show you the next slide, right. Now, when V in equals to VDD, right, when V in equals to VDD, when my input voltage is equals to VDD, at that point of time my NMOS is switched on, right, but my PMOS is switched off because my input is high. So, as you can see in the switch model, if you look here, this is my PMOS, PMOS is basically open circuited, whereas NMOS is closed circuited with resistance equals to R on, right. R on is the transient resistance between source and drain of the MOS device, which, and that is the reason complementary, means both are not together on. Similarly, when V in equals to 0, my PMOS becomes on, and therefore, I have a resistance offered in this manner, and I have my switch model shows me an NMOS to be off. So, this NMOS is off, whereas PMOS is on, right. In this case the PMOS is off and the NMOS is on. So, that is pretty simple and straightforward way of looking at inverter switch model. If you therefore come to the basic fact that the idea here is, therefore, if you let us go back to the previous slide, if you look very carefully, when your NMOS is switched on, right, this V out will have a path and this will be grounded here. So, the output voltage will be 0. When my PMOS is on and my NMOS is off, then this will be voltage will be plugged to VDD and the output will be equals to VDD, which is effectively equals to 1 volt, which means that this inverter allows you to do a peak to peak swing. Peak to peak basically means it is actually swinging from VDD output to 0 output. Such a large range it is allowing you to do. So, we have large swings associated with CMOS inverter switch model, right, and the reason being that you have now large amount of you allow the voltages of the output to go till VDD when my PMOS is on and go to ground when my NMOS is on, right, and that is the reason you get this such type of circuit, and that is the reason you therefore have a very high noise margin available with you and ideally equal to the supply voltage. So, whatever is supply voltage you get noise margin, which means that a static CMOS inverter, right, since it is able to pull your output voltage to logic 1, which is equals to VDD, right, it is utilizing the full support from VDD to ground rail. So, the whole range is being utilized by the input level, right. This is also referred to as a ratio less logic level, which means that independent of the dimensions of this devices, W by L ratios of PMOS or NMOS, I am 100% sure that the threshold voltage will always remain the same it is, which means that once you have fabricated your PMOS and NMOS and attached it as a CMOS inverter using a twin tub process, you will see that your logic is basically a ratio less logic, which means that I do not have to change my W by L of my PMOS or NMOS in order to in order to have different sets of behavior. So, for the same set of behavior as a switch, the same W by L which you are using earlier, you can use it and gives you a very good result here. So, if you go back to your previous case, the ratio-less logic is there, which means that is independent on W by L. Since the output impedance is a low impedance node, it is less prone to noise, and this is a very standard way of looking at it, that whenever an output source is connected to high impedance, you have less noise immunity. When it is connected to low impedance node, the noise immunity is higher and therefore you have less noise at the output mode. The impedance is high, the output impedance, the input impedance is high because I am inserting my signal onto the gate side of those devices. Now, gate is always terminating through a oxide layer or a dielectric layer, and as a result, if you look from the gate side, the resistance offered by the device to input signals are typically very large, right, and therefore, it is high impedance and therefore improved fan out. There is no static power assumption, or even if it is there, it is very small static power consumption is there between CMOS, right. So, we have therefore understood one basic idea. Let me clarify before we move forward, therefore, that two things are very important as far as this structure is concerned, and the two things which are very important are, the first thing is that this CMOS inverter gives you a rail to rail swing, fine. What does it mean, rail to rail swing? It gives me right from VDD to VGND, the whole signal can be used directly, right. So, when my V in is low, my V out, when my V in is low, right, my V out is high, and when my V in is high, V out is low, fine, and exactly behaves like an inverter. It mimics a behavior of the inverter, right, and so on and so forth. So, if you look very carefully, when V in equals to 0, NMOS is off and PMOS is on, right, and we are able to achieve a much better design in this cases compared to the previous cases. With the knowledge therefore, you have gained till now, let us formulate the voltage transfer characteristics of CMOS. Voltage transfer basically means on the x axis you will have V out and on the y axis you will have V in. So, if I vary V in, how does my V out vary? That is supposed to be seen in the VTC of a CMOS inverter. So, what we do is it is very simple and straightforward. We try to find out the drain current characteristics of both PMOS and NMOS and then invert it to get the values, right. If you look very carefully, NMOS has got a profiling in this manner, right, and if you look very carefully, NMOS is always on the this quadrant, right, this quadrant it is there. In a PMOS will be always in the negative and the current will be also negative. So, this is my PMOS quadrant device, right, this is my NMOS quadrant device, right. Then what you do is that you fold it across this spirit in such that you fold it in this manner, right. Once you fold in this and then you fold to this, let us see how it works out. So, I have got something like this is an NMOS, right, and from here I get PMOSs, fine. Now, if you fold this to this side and then fold this to this side, you finally get something which is very close to the voltage transfer, where they cut they will get voltage transfer characteristics. Now, this is NMOS, V in 0 equal to what 1.5, and if you solve it on the right hand side I get something like this. So, this is 1.5, 1 volt, this is 0.5 and so on and so forth, right. When you have PMOSs, you are on the third quadrant, you push it across this x axis, go to this point and then push it across the y axis to go to this point, right, which is this one. So, I get this. Now, if I shift it to the right hand side I get something like this, fine, and therefore, what we get from all these discussion is therefore, if my this module or this module and this module, right, they superimpose on each other, I will start getting a set of points, a set of intersection points in this case, right, instead of intersection points. So, how do I do? This is my NMOS. So, as you can see it is I versus V and this is the curve which you get, right, this is the curve which you get, fine, and this is the curve which you get. Now, when you plot PMOS versus NMOS or PMOS IDN versus or IDP versus V out, I get something like this, right, this is the profiling which you get, right, this is the profiling which you get. Now, wherever these two cut each other, for example, it cuts each other at this point, at this point and at this point, similarly at this point and this point. So, these are the points where the currents from both NMOS and PMOS will be equal and they will be sufficiently important to run the CMOS inverter, right. So, with this knowledge we can safely therefore say that these points which are not available to you will still. So, if you have a NMOS which goes like this, you will still have one point here. If it goes something like this, then you still have another point here, and this will be all your PMOS points. The NMOS points will be directly scaled at this particular limit, right. So, that is what you get out of these differential equations. Once you have done that, now you are in a position to explain the various factors which are there with us, right. Let me therefore come to the previous case and let me therefore explain to you what the issues are. So, now we have done what? We have done the voltage transfer characteristics we have drawn. Anything larger than the voltage transfer characteristics will drive PMOS to heavy saturation, as well as if you do heavy on the inside will be driven into cutoff region, right, and that is what you get from here. Now, if you look at CMOS inverter, you see when my input was low, which is this one, right, my NMOS was off and my PMOS was in the linear region of operation, right. So, let us be very clear about this particular point, that during the point when your input was very low, less than 1 volt or 0.1 less than 1 volt, then we saw that NMOS was off, of course, because it is lower than threshold voltage, and PMOS is in the linear region of operation, right. If you increase your V in and you reach to a region where your input is there but the output is not there, then we define NMOS to be saturated and PMOS to be in the linear region. So, the first was NMOS off, the second is NMOS saturation and PMOS in the linear region, and then what we do is in the third one both NMOS and PMOS in saturation, and then just the reverse happens here. Now, NMOS is in linear and PMOS in saturation, here NMOS is off. So, here NMOS will be on and linear, and this is linear and off. So, you will have off PMOS available with you. So, all the 5 notations which are there in the voltage transfer characteristics of a CMOS appears here as well, right. That is very, very important to be careful about. Now, how I define a switching threshold, right. A very important point, switching threshold, and it is something like this, that if you have a threshold, then it is something like this, which let us suppose this is how I get, right. This is time and this is your profile. Then we say that switching threshold is that value of input voltage at which you would expect to see a change of state in the output side. Typically, the ideal value of switching threshold is is basically VDD by 2. So, if you are applying a VDD of 1 volt, typically switching threshold critical can be written as 0.5. So, if your input voltage is just below 0.5, please read it as 0. If it is greater than 0.5, please read it as 1, right. So, we have understood what is the difference between a switching threshold and positive switching threshold, in this case to be switching threshold, right. So, we have understood CMOS inverter working principle, CMOS switching threshold, what is the meaning of switching threshold, and CMOS inverter noise analysis. We have also understood basic fundamental principles that dV out dV in should be 1, which means the amplification should be 1 for finding out the values of the other variables. Now, let me explain to you the basic, as I discussed with you, the MOSFET inverter principles, and therefore, they are divided into 5 regions. The middle region, which is the green one which you see here, is basically the region which is highly unstable, because a small shift in the input will result the Q point to shift either to the top or to the bottom. Top bottom means this point or at this point, right. So, you have to be very careful while dealing with analog or mixed signal blocks, because they force the output to either go to VDD or go to ground, right. Whereas, your job in this stage is, yes, you need to go to high VDD and low VDD, but then you have to be very cautious in the terms that you are stable also in that value of voltages, right. So, when VDD goes to NMOS off in linear region, and in this case NMOS to be in this NMOS to be in the linear region, whereas here PMOS was linear region. So, this was PMOS linear region, this is NMOS linear region, right, and it works fine for any other circuitry which you see. As I discussed with you just beforehand, that when you plot this graph, so what I was trying to tell you is that this is being cut. So, this is NMOS and this is PMOS, they are cut at various points. The first point is this one, NMOS and PMOS, then you have this point available with you, then you have got so this point and so on and so forth, and on this side you will have this, and then you will have this and so on and so forth, right. And therefore, for various gate voltages, V in my gate voltages, I start getting a new value of input voltage, and these input voltage are strong functions of the output voltage. As you can see here, therefore, this is for V. So, for the same VGS, so this is my VGS1, right, GS1, VGS2 and so on and so forth, and these voltages are same for both NMOS and PMOS, right. Now, we have understood therefore the various regions of operation. Let me see how we obtained switching threshold from the VTC of the graph, right. The VTC is given after switching threshold. Please understand, your devices will be in linear region of operation whenever you are in either region A or region C or region E of the major issue, or maybe I will just show you. Okay, I will just tell you that. So, what I will show is to you is that my VIL is nothing but this whole quantity which you see in front of you. How did you find out VIL, and we will show you that doing that, but let me come to therefore. So, understand that Vm is given by this quantity, right, where R is basically the ratio of Kp to Kn, Vd sat P upon Vd sat n, right, and that is also equals to V sat P Wp and V sat n Wn. So, these are the 4 parameters which are there, and we should appreciate the fact that all the transistors, if you want to find out both the transistors in saturation, right, and therefore, we say that K n Vd sat n, right, into Vm minus Vth. Vm is nothing but the applied gate voltage minus Vth minus Vd sat n by 2, right. So, this Vd sat n by 2 is a fixed quantity available with you. Similarly, this are all fixed quantities, and from here you can obtain the value of Vm or switching threshold, right, and they are given by this formula for the switching threshold Vtn plus 2 Vds sat n plus R and so on and so forth. So, as you can see, higher the value of Vd sat, higher will be my switching threshold. Now, let me come to the CMOS inverter. Inverter is very simple and straightforward. If there are 2 inverters connected in this manner, right, they connected in this manner, then if you apply a 1 voltage here, I will get a 0, I will get also a 1 here. But let us suppose by mistake I give it 0, then this will be 1, this will be 0, right. So, this is my VDD, output characteristics input, and this is logical high range as I discussed with you. This is logical high, which means that having any particle or issue with voltage range in this value will be unstable, and therefore, it will not be available to you in the literature. Whereas, if you take care of low noise margin, we assume that NML equals to NMH, which means that the low noise margin NML is exactly equals to NMH, which is the high noise margin, right, and you do have this at this region effectively available to you. Now, we define therefore, the NML is equals to VIL minus VO. What is VIL, right? Let us understand what is VIL, right. Let me explain to you what is VIL. VIL is basically meaning, as the name suggests, it is VIL is V input low, right. Whenever my input is low, so if you look very carefully here, when my input is low, output is high, when my input is high, output is low. So, when my input is low, I would expect to see that my output is high, and similarly when my input is high, my output is low. With this knowledge, we define Vi. So, we define low noise margin NML as VIL minus VOL, and this is input low minus output low, and NMH basically is output high minus input high, right. And therefore, this NMH takes care of the high values, one higher probability of values, whereas NML takes care of zeros and lower probability values, right, and so on and so forth. As I discussed with you, since VOH equals to VDD, so I get so NMH will be VDD, right, minus VIH. VIH is basically equals to V, let us suppose VIH. So, my NMH is equals to VDD minus VIH, and my NML is just equals to VIL, because VOL is in any case 0. So, I get NML equals to VOL. So, I get NML equals to 0 or equals to VOL, and the second case I get NMH equals to VDD minus VIH, right, and that is what we have understood or given a process an idea. So, how to calculate VIL? Well, by definition, when VIN equals to VIL, NMOS transistor is in saturation and PMOS is in the linear region, right. So, just the onset of saturation for NMOS, and for PMOS it is a linear region of operation. And we also know, and this is quite interesting, and I would like you to appreciate this point, that dV out dV in is equals to always minus 1, right. So, you have to be very cautious that when you are calculating VIL, you have to assume that my input and output are exactly equal. If they are not, you have to first make it equal in order to find out the value of current, which is in this case IDN equals to IDP, right. So, therefore, in saturation mode I know Kn by 2 VGSN minus VSN whole square must be equals to Kp by 2, then this is a non-linear region of operation. If you remember, I think it is clear to you. So, in this problem or in this solution to the problem is that you do have a fixed value of gate voltages and your applied voltages, but the input signal will tend to change it slightly whenever the output signal is above, when the output signal is above VDSP. So, we know VGSP is equals to Vin minus VDD and VDSP is equal to Vout minus VDD. If you solve it, I get this big equation which is available to me. If you take a derivative with respect to VIL, then both sides will satisfy VIL condition. So, I get this equals to this into this plus this plus this. So, I get this as the workable solution for this VIL input low. So, we have learned two things. What is input low? Input low is the voltage at which the output is high, right. CMOS inverter calculated in VIL, VIL is basically this point. So, what I say is that this equals to Kp by 2, this whole thing plus this minus this minus this minus this dV out dV in, right. And if I place dV out dV in equals to minus 1 V in equals to VIL, I get a big equation like this, which can be actually downtrodden to VIL to be equals to this much. So, relatively Kr is basically Kn by Kp, process transfer parameter for N and P. But if these are okay and if these are fine, the values of parameters are extracted fine manner, we can say that VIL is given by this equation, fine, and it depends on the value of Kr, it also depends upon the value of V out and VDD, right. If you want to calculate the value of VIH, then that VIH is input high, which means that whenever my input is high and output is low, anything larger than that it is not expected from you. So, if I solve it, that grade is exactly the same, VGSP minus VTP whole square is equal to this whole quantity. Similarly, for a Vn minus, so for a beta value or a breakdown value, I get this into consideration, and if you take the derivative of both sides, I get VIH as some value, VIN is equal to VIH and dV out equals to dV in. If you solve it, I get VIH equals to this quantity which you see in front of you, right. This is the value of V out, but this would not have come out if we did not do the derivation properly in your previous case. The voltage transfer characteristics varies in this manner, that for nominal when Kr equals to 1, I get this, the black one is the nominal one and it is almost constant, almost giving a fall. But if you take good NMOS or good PMOS and bad NMOS, then the transfer characteristic shifts to your right, whereas if you take good NMOS and bad PMOS shifts to the left. Good bad variably means that when you say good PMOS, does it have, I said it is good if and only if it has got a pull up capability to VDD. Similarly, an NMOS can be said to be good provided it is able to push down or pull down the voltage to ground, right. So, none of them were able to do so, and therefore, I can safely say that this is a good PMOS, right, and therefore, shifted to the right with high switching threshold, and this is good NMOS and the lower switching threshold, right. So, this is Kr less than 1 and Kr greater than 1. Kr is basically Kn by Kp. So, when a Kn by Kp is less greater than 1, I shift to the left, and when this is less than 1, I shift to the right, right. And the nominal value is Kr equals to 1, means Kn equals to Kp, which primarily means that PMOS and NMOS have equal pulling capacity. From the same graph, see then if I say from this graph, you can see that I can switch from this point to this point and I can go from logic 1 to logic 0, right. This is output logic 0 and this is output logic 1, which you see. But then somewhere in the middle, obviously the gain here will be 0 and the gain here will also be equals to 0, but somewhere in the middle your gain will be a strong function of your V in, because if you remember AV is equals to dV out, right, dV in, and that is what you get here. So, dV out dV in write down and you get this big expression which is important in front of you. Now, if you ignore the second order term and putting V in equals to Vm, Vm is the switching threshold, then I get G or the gain to be equals to this big quantity which you see in front of you, and it is given by this quantity which you see here. It depends upon all these factors and so on and so forth. So, therefore, gain is purely determined by the technology parameter and it slightly depends upon the transistor sizing ratio, right. So, it depends very small on the sizing ratio and it is mostly determined by the technology parameters and not by the structural parameters of the device, right. As you can see here, therefore, for varying values of VDD, I would expect to see. So which means that the VDD is moving in this direction. Higher the value of VDD, higher will be the switching threshold, and lower the value of VDD, lower will be the switching threshold. I hope you have understood why is it. Similarly, if you do a plotting of the graph between various values of V in, then automatically those values of V in which has got higher values of V out will be shifted to the right, and vice versa will be for the blue and black and red onto the left, right. And that gives me a good idea. It gives me therefore that by making my inverter pull up and pull down. So, why we define, so my PMOS is referred to as pull up, and my NMOS is referred to as pull down, fine. Pull up and pull down. Why pull up? Because PMOS is pulling the voltage to ground to the VDD, and NMOS is pulling that to ground, and therefore this is a pull up device and pull up. So, we define the PMOS to be as pull up device, and below one we define as pull down device, right, and we get this substrate configuration here. So, let me recapitulate what we did. CMOS consists of a PMOS block and an NMOS block. An ideal inverter has got a high input impedance and 0 output impedance. The logic swing is equal to supply voltage and does not depend upon the device relative size, and the gain the inverter is mostly a function of the technology. I hope you have understood what we have discussed in this lecture. We will come back with another series of lecture on the CMOS basic inverter part 2, right. Thank you, thanks a lot, thank you very much.